Hi, this is a Hyundai i30. It's a G4 FA engine, dual overhead cam, 16 valve, MPI, GD, and it's got variable valve timing. What I'm going to show you is the location of the upstream and downstream heated oxygen sensors. They're located at the back of the engine on the manifold, and that's where you'll see the catalyst and the two oxygen sensors. So I'll go in and show you the best I can to their location. So as we go into towards the back of the engine, you'll see a heat shield there and a cable there in two positions, and then these are the connectors at the side there for the oxygen sensors. So we'll come round slowly. You follow that cable along to the side, and that is the upstream sensor. So that's pre the catalyst, and then right at the bottom, probably quite hard to see. I'm going to zoom in and show you in a second. Right at the bottom there is the downstream sensor, heated oxygen sensor, and the wiring. Let's see if we can get in there. There it is there. It's clipped in two positions also going down to the downstream, and that's after the catalyst. Okay, what I'll do now is zoom in and you can see close-ups of the locations of them. I'll show you the pre-cat one first at the side here, so I'll zoom in and show you that one. Okay, so there you can see that's the pre-cat, the upstream heated oxygen sensor there, and the wiring, associated wiring. So if we come out, you'll see going across here the heat shield of the manifold, and then going to the connectors there. And what I'll do now is show you the downstream one. I'll get in as close as I can. It's in a more awkward position, downstream. Let's see if we can get in there and see the location of the downstream oxygen sensor. And that one is after the catalyst. You can't see the catalyst here because of the heat shield over the top there, but that's the downstream heated oxygen sensor there. So that's the location there, as you can see. I'll come out, see I'll get more of an understanding there. Okay, and we'll go to the wiring here where they connect up. So here's the wiring here connecting. So this is the top one here is the upstream sensor, pre-cat. The bottom one there is the downstream. The 4-wire oxygen sensors. If you look at the colours there, you'll see the two white cables. They're the heater. They're the heater wires. The black one there at the top is the signal, and there's one at the bottom there which is hard to see, which is a grey wire. The grey wire is the ground. And these are Bosch sensors that are fitted to the car, and that's the wiring layout of them. So hope that's helpful to show you the wiring there. The two white ones heater, black one's the signal, and the grey one is the ground. So there you go. So this upstream sensor here, pre-cat, is known. This is known as Bank 1 S1. That's what it's known as. The pre-cat sensor, Bank 1 S1. It's used to determine fuel control when the sensor is up to temperature, basically around 600 degrees. It enters a closed loop condition. Okay, so, and then what happens is then it generates a waveform. The signal oscillates above and below 450 millivolts, and a good oxygen sensor tends to have even waves of 150 millivolts to 850 millivolts range, while ascending and descending in cycles of, within 100 milliseconds when it goes closed loop. So with a pre-catalyst oxygen sensor, when the sensor senses a rich mixture in the exhaust, the PCM, the powertrain module, takes that information and it tries to do the opposite to make the fuel mixture that is called lambda, trying to get the perfect lambda by sending fuel trims in the opposite direction. So the same is true when the oxygen sensor senses a lean mixture in the exhaust. So when this occurs, the PCM module takes this information and adds fuel trim to enrich the air-fuel mixture in order to achieve lambda again. So the exhaust gas oxygen sensor provides precise indication of stoichiometric air-fuel ratio. So in a petrol engine, it's 14.7 to 1. So that's 14.7 parts of air to 1 fuel. So at a stoichiometric point, it produces 450 millivolts. The heated oxygen sensor, that's what it does, or exactly a lambda of 1. So that's your pre-cat oxygen sensor. So that's what it. So there you have the post-cat oxygen sensor. So that's bank 1 S2. That's what it's known as, and it shouldn't oscillate like the pre-cat one does. So it won't oscillate at all, and it's merely to determine if the catalytic converter is doing its job. That's what it's doing. So if you get both oxygen sensors showing identical readings, it's very unlikely anything other than a bad catalyst is the cause. So that's the post catalyst downstream one that you're looking at. So bank 1 S2 as it's known. So if you look at this graph here, this is showing normal operation of the pre-catalyst sensor, the upstream sensor. So that's bank 1, sensor 1. As you can see there, it's oscillating. So that's when it's in a closed loop condition. That's what you will see on your scan tool. Ideally, we've got there 0.45 in the middle there, and it's switching constantly all the time when it's in a closed loop position. So as you can see there, it's going from 0.3 there to 0.6 on the scale there, and it's going above it. What it's trying to achieve all the time in normal condition is the fuel ratio of 14.7 to 1 in a petrol engine. That's what it's trying to achieve, the car all the time, and a lambda of 1 ideally. So that's what it shows, what you'll see at normal operation. Exactly that waveform is what you want to be seeing on the car. So to achieve this 0.45 constantly all the time, what's going to happen is this oscillation is controlled by the PCM module. So when we get to 0.45 a volt here, and we go past it, we're starting to go rich. So what happens is straight away the PCM will command the fuel injectors to go lean, because we've gone past the stoichiometric ideal ratio that we've got, stoichiometric ratio. So what happens is, as soon as we go past 0.45 here, we're going rich. So so the PCM detects that straight away and wants to go lean. So that'll tell the fuel injectors to go lean using pulse width modulation. So the short-term fuel trim, as it's going rich, will go negative. Short-term fuel trim goes negative. We go past 0.45. Now we're going lean. That gets detected as soon as it goes past that point there, the ideal ratio, which is 14.7 to 1. So as soon as it goes lean, then the PCM detects that and straight away wants to go rich again. So what it does to do that, when we go lean, the short-term fuel trim will go positive, and this happens very quickly. So you might see on your short-term fuel trims plus and minus changing very quickly, but you know, it'll only be by 2 to 3, going plus 3 or minus 3. That's what you'll see. So that's normal operation of the oxygen sensor, the upstream one. That's how it operates and how it works. If you had a bad sensor, you have reduced cross counts. So as you can see there, there's your 0.45, and we're not going up and down as much. You know, from there, from lean to rich, it's a lot smaller. So you can see that's a reduced cross counts there of a bad sensor. So that's what it's showing. Now, if you want to look at this one at the top here, this is when the engine is running rich, and you can see there's your 0.45. We're basically more at the top end there than we are at the bottom, so that's showing the engine running rich there. Running lean, you have a high O2, and basically it's below the graph there. So that's showing the graph when the engine's running lean, and you'll get a high O2.